Welcome everyone. So this is the course unit, Power Electronics. Today is the very first lecture we're going to be having. It's going to be a brief introduction to what Power Electronics is, what are we yet to cover in the consequent 4 months of the semester, that is academic year 2, semester 1 DEE. On behalf of Uganda Institute of Information and Communications Technology, UICT, under the eCampus program. I'm going to be your lecturer throughout the course unit for this semester. And let's kick off with an introduction or a definition of what power electronics is. All right, this is lecture 1. So let's look at the definition of power electronics. So this is a branch of electrical engineering, This is a branch of electrical engineering that deals with the manipulation of electrical power, that is voltage and current, as we will see, with the help of semiconductor devices like diodes. We know what diodes are. Diodes, transistors, a couple of types, BJTs, MOSFETs, JFETs, UJTs. We'll look at them, IGBTs. Transistors, thyristors, or silicon controlled rectifiers, as we'll see, or controlled diodes. We can't skip mentioning triacs, diacs, and so on and so forth. Remember, we said it's a branch of electrical engineering that deals with the manipulation of electrical power, VI, one of those, with the help of semiconductor devices like diodes, transistors, thyristors, triacs, and so on and so forth, and passive components like good old capacitors. Passive components are ones that require no extra voltage for them to fulfill their operation. Like transistors are not passive components, they're active components. They need a separate power supply, power source. We'll look at those details in the consequent lecture. So capacitors, resistors, and preferably inductors. So power electronics is a branch of electrical engineering. It's a branch of electrical engineering that deals with the manipulation. Mark the word. Manipulation simply means changing, making changes, manipulation of electrical power with the help of semiconductor devices like diodes, thyristors, blah, 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 blah. And passive components like capacitors, blah, 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 blah. So we know what those are, because we're going to have a special lecture only discussing the details of each and every component, passive or otherwise. So the moment we walk into that branch of electrical engineering whereby we are most interested in manipulating. So manipulation in layman's term, manipulation could also interchangeably be used with another term, manipulation, making changes or modifying, making changes. So these two terms could interchangeably be used. So manipulation of electrical power with the help of semiconductor devices like diodes, transistors, thyristors, triacs, and more on, so on and so forth, and passive components like capacitors, resistors, and inductors. So if we use a combination of these to manipulate or to make changes to electrical power that is being delivered to a circuit or being dissipated by a load, because power can be delivered and dissipated or used. So if we manipulate those parameters, and it's not only voltage and current we will be manipulating, because it depends on the power source. If it's AC, we have a lot to manipulate in that scenario. We can even manipulate the switching times. I don't want to get ahead of myself at the moment. So, long story short, we're going to be dealing with our power equations. So, for ease, let's say we have a DC circuit. So, and we happen to have a resistive load R and a current I flowing, right? And the voltage drop VR across it. So, the power dissipated by that load could easily be given by, so let me turn this into a simple capital I IV. In this case, IVR. So the voltage drop across that load, let me represent it with an appropriate circuit whereby the voltage drop across this resistive load R that's conducting a current I, it's the same all throughout, happens to be having a voltage drop of VR. So this would be the power dissipated. So this is the power dissipated by that resistive load. For ease, I've used a resistive load. For ease, I've used a resistive load. For resistive load, that will be its power dissipation. That's interesting. So let's look a little bit at what this equation means. You know, in engineering, we represent very many real-world phenomena and systems with equations. So as engineers, technicians, our job is to interpret them into layman's terms. So this simply means this equation tells us one thing. That power is directly proportional to the current flowing through the load. For that, we can agree direct proportionality. Power is also proportional to the voltage drop across that load. So the more voltage that drops across this, if it was a heater, for example, let's say it was a heater, a load, a resistive load like a heater, the more voltage you drop across it, the more heat it will generate, or the more power it dissipates. The more current it draws, the more power it's dissipating. Let's look at an interesting thing. So let's say since it's a heater, it's giving off heat, we needed to manipulate how much heat. Here the word manipulate coming back again. So okay, let me just do it like this. Yep. So we need to manipulate the amount of heat that is being radiated by the heaters. Let's say this is in a factory. Let's say we are baking bread on an industrial scale. Let's say space heating, we are heating up space, let's say in a poultry farm. We need to keep our poultry or our birds warm. We need to adjust heat, the amount of heat saturating in the environment. So, and we realized that for that much we know, the amount of heat being dissipated by this heater is also proportional to the power it dissipates. So that means if we get to control or manipulate the power, we can manipulate the heat source or the amount of heat in the area. So, and we realize that power is proportional to the current through a load. The same power is proportional to the voltage drop. So the voltage drop, VR, is equal to the I going through the load and its resistance. So the multiplication between the current going through the load, so current must flow. Current must flow for us to have a voltage drop. So if the current flowing through the load is 0, let's say 0 times R just remains 0 volts. So if we go back to the power dissipation equation, P is equal to 0 times VR. 0 times VR. So this tells us we will never have power dissipation if we don't have current flowing through a load. These are very basic facts I want us to have on our fingertips before we proceed. These are basic facts I want us to have on our fingertips. So this tells us we have 0 watts. Remember, this is a DC circuit. I decided to choose a DC circuit for ease. 0 watts. So if we are to manipulate the power, we must make sure the current does not go to 0 volt, to 0 amps. 0 amps, let's say I, in this case is 0 amps. So we must make sure we don't have 0 amps because we'll have 0 power. So let's say I is some other value, is not 0. It's not 0. So how do we manipulate I? Remember now, I in that circuit is given by the voltage drop divided by the resistance of the load. Very important. Divided by the resistance of the load. So we've realized if we are to manipulate power, we can manipulate I or V. So let's look at which one can we easily manipulate. So we are looking at how to calculate the current through the load. We have the voltage drop across it. Let's say we've measured it with a voltmeter or a multimeter. We know the resistance, then we are looking for the current. So this becomes our current. So if we are to manipulate power, we manipulate current. If we are to manipulate that current, we manipulate voltage. All right, that's simple. That's very, very important. We have to manipulate the voltage drop across. I have to manipulate the voltage drop. So let me rewrite it around here. Okay, let me rewrite it here. I through the load is given by the voltage drop of that across the load divided by its resistance. So we are to manipulate this upper parameter because the resistance is fixed. Resistance is fixed for an ideal load. The resistance is fixed. So the only parameter remaining that can easily be manipulated is the voltage. So this concept alone is going to drive a huge section of the entire course unit, whereby we'll look at voltage conversion circuits or power conversion circuits, whereby we have a circuit that converts DC, AC, DC to DC, AC to DC, AC to AC. So the idea that we can play around with the voltage, keeping this fixed, we can manipulate the current through a load, thereby manipulating the power that's being dissipated by a load. So these equations can change. This equation can change depending on the load type. It could be RL, RLC. We could be dealing with DC and we are looking at transients. We could be looking at AC and we're looking at apparent power, real power, and other things, power factor and other realities that come with electrical engineering in that setup. So let's hope we've understood that. So what do we use? What do we use? We've talked of semiconductors. We've talked of semiconductors. So we will manipulate that voltage. We will manipulate that voltage. Sorry for cramming the board, but that's my style. So what are we going to be using? We've said we're manipulating, so we found out that it is easy to manipulate the voltage. We are going to be manipulating the voltage drop across the load. So what are we going to be manipulating it with? A couple of semiconductors like diodes, clamping and clipping circuits. That's nice. We have thyristors, call them silicon controlled rectifiers. This is an uncontrolled rectifier. This is a controlled rectifier. So we have triacs. These are for AC circuits. These are for DC circuits. So we have diacs. So these are not the only devices. So we can have transistors. Of different types for different reasons. So we are going to pull this off with semiconductors and passive components like capacitors, resistors, or even inductors. Very many components in electronics fall in this category. It's either resistive load, capacitive, inductive, or it's a thyristor, a transistor, a diode, diodes, triacs, and very many concepts. So we combine these, we can have circuits that help us manipulate voltage to manipulate power. Or we will see we'll have even circuits that help us manipulate current directly, like techniques like current chopping. We will look at that. We will cross that bridge when we get there. So this is how the whole paradigm works. So we will look at things like how much power did we start with? Let's say we have an electrical system that takes in power input, and gives us a certain power, a power output. Let's say we bring in 100% of the power, and this electrical system, whatever, this could be a circuit that helps us manipulate. This is the circuit that's going to help us do the manipulation of voltage or current, and current. So So it's a power conversion circuit. So this is a power conversion circuit. So let's say we give it 100% of whatever we had. Let's say 10 watts, 100 watts, whatever. Then when we measure the output power, it is just a fraction. It's just a fraction of the input. So P out is equal to some fraction times the input power. P in, it's some fraction times P in. So let's make K so ideally, mark the word ideally, in an ideal situation, this fraction whichever we choose to look at it, will denote a very important term called efficiency. So efficiency is just a measurement, an electrical measurement that shows how much power we can give to a system versus how much it will allow on the output. Very important, very, very important. This is a very important parameter that we use it all the way through the electrical engineering paradigm. So we will look at things like power, manipulation, that is manipulating voltage and current. So that's what will lead us to power conversion circuits. That's a huge section of the entire course unit. We'll have power converters. We will look at the terms like efficiency. We'll learn how to compare efficiency of different power conversion circuits. We will see very many more details that come with manipulating power. The reality is, why are we having in 100% and we're getting a fraction on the output of the power to a given conversion circuit? We will look at the realities that come with using these components to manipulate. Nothing is free in the universe. So we manipulate power at a cost. Transistors are not ideal. They have power losses of their own. Capacitors are not capacitors all the way. It depends on the switching frequency. They could easily behave like an inductor. Yeah, an inductor can easily behave like a capacitive load. So we are to look at diodes. We are to look at thyristors. These components are not ideal. So I don't want to get ahead of myself for now. Allow me to stop here. We're not going to be having very, very long lectures. We're going to be having short lectures, but in a series format. So thank you for being good and attentive learners. See you in the next lecture.